So we are discussing bending moment for uniformly distributed load in this video. Uh, to discuss the entire topic in one video is a bit difficult and will be too long video, and therefore I have split this topic into two videos. And at the end of the two videos, you will be able to calculate the bending moment for a uniformly distributed load, locate the point of maximum bending moment in the beam, calculate the value of the maximum bending moment, and then draw the bending moment diagram for the uniformly distributed load. Now, let's start with a beam with a given uniformly distributed load. Um, as in the previous cases, let's assume the beam is simply supported at A and B, where you have reactions Ra and Rb at the end points. The beam has a load of 10 kilonewton per meter, uniformly distributed over a span of 4 meter, and you also have 1 meter either side of the uniformly distributed load to the reactions. Now, the total load of this force system is 10 kilonewton per meter acting over a span of 4 meter, and therefore the total load is 40 kilonewton. And we have discussed in previous videos that for the purpose of calculating the reactions at A and B, the effective load of this UDL can be assumed as acting as a point load at the mid-span of this length. So we can assume the effect of this uniformly distributed load as acting as a point load at the midspan of this length. So that is 2 meter from this point here. So now we have a point load of 40 kilonewton acting at 3 meter from A. From the equations of equilibrium, we have Ra plus Rb is equal to 40, and moment about A, if you take moment about the point A, you have total distance to B is 6, so 6 Rb moment about A equal to 0 gives 6 Rb minus 40 kilonewton acting at 2 plus 1, 3 meter from A, acting downward and therefore creating a clockwise moment opposite to the anti-clockwise moment created by Rb. Therefore, minus 3 times 40 is equal to 0, or Rb is equal to 120 over 6, that is equal to 20 kilonewton. Now if you substitute this 20 kilonewton in the equation here, you can calculate the value of Ra. Is Rb equal to 20, and therefore Ra equal to 20. So you have Ra equal to Rb equal to 20 kilonewton. That is the reactions. Now to calculate the bending moment, we use the method of sections. So you take the first section at or first section between point 1 and 2. So you have point 1 here, 2. So your first section will be here. You have a section XX, reaction Rb, distance x. So moment about the point or this section, you always take moment about this point. So moment about the section equation is Rbx, Rb times x, and you have two values for x, 0 here and 1 here. X varies from 0 to 1. So at x equal to 0, which is this point, the moment equal to Rb times 0, that is equal to 0. That is your moment for point 1. Now at x equal to 1, which is this point, moment is Rb times 1, that is 20 kilo Newton meter. So you have your values, the moment values for 1 and 2 here. Now moving on to the next section, which is in between the uniformly distributed load. So you take the section somewhere in this. So what you have is a reaction at B, section here, this point, and you also have a portion of the UDL. So this is 1 and this is x. Now taking moment about the section, you have moment about x is equal to Rb acting at a distance of 1 plus x. So that is Rb x, creating a counterclockwise moment. And now again you have 10 kilonewton per meter acting over a span of x distance. So total load of that will be 10x. And again, for the purpose of calculation, we can assume this as a point load acting at the midspan. So the distance of the point load from this point will be, the distance d will be x by 2, because the 10x, the total load, will be acting at the midspan of the x, and that's why you have x over 2x by 2 from this point. So the moment will be creating a clockwise moment because it's a downward force, clockwise moment, and the magnitude of the moment will be 10x times x by 2. This is the load, this is the distance. So your moment equation is Rbx minus 5x squared. Now the value of x varies from 0 here to 4 here. So at x equal to 0, moment is Rb times x, and this this is Rb times x plus 1. You know, Rb is acting at 1 plus x from this point. So you have x plus 1. So moment equal to, at x equal to 0, moment is Rb, because this time becomes 0, and at x equal to 4, moment is 5 Rb minus 5 into 4 squared, that is 80. So that will be 100 minus 80, that is 20 kilo Newton meter, and this 2 is 20 kilo Newton meter. So that is your the moment at this point, that is point 2 and the point 3. So you have point 2 and 3 here. Now taking the section in between the other two force changes, you will need to take a section here somewhere in between these. So what you have is your Rb, the uniformly distributed load, and your section. So this is x, this is 4, and this is 1. Now the the moment about X. Again, always you take the moment about this section here. So moment about that point is RB acting at 5 plus X. So RB times 5 plus X minus 10 kilonewton per meter acting over a span of 4, that is 40 kilonewton acting at the mid span as a point load. So that will be 2 plus X. 40 times 2 plus X, and that's it. That's all the load. There is no other load in the towards the left or in this area of the section. So again, your section varies from x equal to 0 here to x equal to 1 here. So at x equal to 0, the moment is RB times 5, that is 5 RB minus 80, that is equal to 5 RB is 20 minus 80, that is 20 kilonewton meter, and at x equal to 1, moment is 6 RB minus 120, that is 120 minus 120, that is 0. So that's your third and fourth values of moment. So your third point here and the fourth one here. So this is your third and this is your fourth moment value. Now as you can see, in each equation, the last value of the last moment value calculated will be the first one in the next section. For example, you have 1 and 2 here. So the second value of x in this section, which is x at 1, will be same as the first value of x in this section. So that is the point 2 again here. So the magnitude of the moment also should be the same. That is, your 20 here should be the same as the first value of the next one, and this 20 should be the same as the first value of the next one. And normally you get 0 moments at the ends. So 0 at point 1 here and 0 at point 4 here. So you have 4 points. 0 kilonewton meter, 20 kilonewton meter, 20 kilonewton meter, and 0 kilonewton meter. So we have calculated the bending moment of the force system in this video. Now this part is done. You will see how to locate the point of maximum bending moment and calculate the maximum bending moment, and also to draw the bending moment diagram for this force system in the next video. So do watch the next video to complete this exercise. Thank you for watching.